In the 3 weeks after Christmas of 2022, the San Francisco Bay Area recorded more rainfall than in any 3-week stretch in 161 years. To find a wetter 3 weeks, you would have to go back to a year when the President of the United States was Abraham Lincoln, when California was not yet 15 years old, when the telegraph was still the fastest way to send news across the country. That is how far back you would need to travel to find rain like this falling on the same hills, the same rivers, the same small towns that flooded again in the winter of 2022 into 2023. No hurricane made landfall. No named tropical storm crossed the coast. The system responsible for this had no eye, no spiral bands, nothing a satellite technician would have flagged a generation ago as dangerous. It was invisible in the way that matters most, not hidden, just unrecognized. Meteorologists have a name for it now, and once you learn to see it, you will notice it every winter on the weather map. A long, gray brushstroke reaching across the Pacific like a spilled river of ink. It is called an atmospheric river, and the ones hitting California are no longer behaving the way the textbooks said they would. By the end of this, you are going to understand exactly what an atmospheric river is, why one storm system can carry more water than the largest rivers on Earth, why a nickname involving tropical fruit became shorthand for some of the most destructive weather California has ever measured, and what a group of research scientists discovered when they flew an aircraft directly into one of these things and recorded a number that, for a moment, nobody quite believed. We are also going to get into the part almost nobody outside a handful of climate labs is talking about yet. The specific mechanism by which a warming ocean is turning an ordinary winter storm system into something closer to a fire hose bolted open at both ends. Before we go further, if stories like this, the ones that take you inside the actual mechanics of the planet, the sky, the ocean, and the ground beneath your feet, are the kind of thing you want more of, this is the place for that. Subscribe now, because storms like the ones we're about to walk through are not slowing down, and neither is the science trying to catch up with them. We'll be right here tracking it as the data comes in. Tell me where in the world you're watching this from, and whether an atmospheric river has ever reached your own coastline. Now, let's get into it. Start with the plain, almost embarrassingly simple fact that took meteorology decades longer to formalize than you would expect. The atmosphere carries rivers, not metaphorically, in the loose sense that a poet might use the word. Actual, physical, continuous corridors of water, flowing thousands of feet above your head, with defined edges, a measurable width, a direction, and a volume. Atmospheric rivers are relatively long, narrow bands of highly concentrated water vapor flowing high above us in the atmosphere, and are the largest transport mechanisms of fresh water on Earth. They do not look like rivers to the naked eye. From the ground, an atmospheric river just looks like a very insistent gray sky. From space, using instruments tuned to water vapor rather than visible light, it looks exactly like what it is named, a long ribbon, sometimes stretching from the tropics all the way to Alaska, curling and bending with the jet stream the way a real river bends around a valley. An average atmospheric river, nothing special, nothing record-breaking, still carries a staggering quantity of water. While atmospheric rivers can vary greatly in size and strength, the average atmospheric river carries an amount of water vapor roughly equivalent to the average flow of water at the mouth of the Mississippi River. Sit with that for a second. The Mississippi, at its widest and deepest, disgorging into the Gulf of Mexico, is one of the defining rivers of the North American continent, and an unremarkable atmospheric river matches that entire discharge, except it is doing so while suspended in the sky, invisible, moving at highway speed toward a coastline that has no idea it is coming until the first drops start to fall. And that is the average case. Exceptionally strong atmospheric rivers can transport up to 15 times that amount. The scientific credit for naming this phenomenon goes to 2 researchers at the Massachusetts Institute of Technology in the early 1990s. The term atmospheric river was first used in the 1990s by Massachusetts Institute of Technology researchers Reginald Newell and Yong Zhu, who were studying the bands of rain that travel across the Pacific Ocean from Hawaii to California. Before that formal christening, forecasters on the West Coast had already been living with the phenomenon for generations, without a unifying theory to explain it. They called it A Hawaiian storm. They called it, more evocatively, the Pineapple Express. And long before either of those names existed, California's earliest American settlers simply called it disaster, without needing a scientific term for what was drowning their new state. So we have established what an atmospheric river physically is: a long, narrow, moving column of concentrated water vapor, several thousand miles long, a few hundred miles wide, roughly 2 miles thick, carrying a river's worth, sometimes 15 rivers' worth, of moisture that has not yet fallen as rain. That's the plumbing. What we have not yet answered is the harder question, the one that actually decides who floods and who doesn't. Why do some of these things drift ashore as a gentle, beneficial soaking that fills reservoirs and quietly ends a drought, while others turn into the kind of event that swallows entire towns? The difference between those two outcomes has a name too, and it starts with a fruit that has nothing to do with California, and everything to do with why the state's most dangerous storms keep tracing the exact same path across the open Pacific. There is a reason the most feared version of this phenomenon carries a name that sounds almost cheerful: Pineapple Express. It sounds like a roller coaster, or a cocktail, or the name of a food truck, not a weather event capable of tearing hillsides apart and drowning valleys. But that mismatch between the name and the menace is exactly the point, and understanding why requires going back to where the moisture actually originates. A well-known example of a strong atmospheric river is called the Pineapple Express, because moisture builds up in the tropical Pacific around Hawaii and can wallop the US and Canada's west coasts with heavy rainfall and snow. Picture the ocean surface near Hawaii on a warm winter day, not the postcard beaches, but hundreds of miles of open, humid, sun-warmed Pacific water, quietly evaporating moisture into the lower atmosphere hour after hour. Under the right steering pattern, the jet stream reaches down, grabs hold of that reservoir of tropical moisture, and stretches it into a corridor, pointed like an arrow straight at the California coast. The jet stream in the sky transports humid air from the Hawaiian Islands toward California, and because the stream is filled with moisture, it can bring torrential downpours to California and heavy snow to the Sierra Nevada in the winter months. The first thing that should stop you about a Pineapple Express isn't the volume of water, it's the temperature of it. This moisture did not originate over the Gulf of Alaska or the frozen North Pacific. It came from the tropics. It is warm. And when warm, saturated tropical air slams into the cold air already sitting over the mountains of California in winter, the temperature contrast forces a violent, rapid condensation, the atmospheric equivalent of fogging up a cold window with your breath, except scaled up to the size of a state. That condensation releases enormous amounts of latent heat, and that heat is fuel. It intensifies the storm from the inside, in the same way that a bonfire fed a steady stream of dry kindling burns hotter and faster than one left to smolder. This warmth creates a second, quieter danger that is arguably more destructive than the rain itself. It eats the snowpack. A cold Pacific storm off the Gulf of Alaska drops snow in the mountains and moves on, banking frozen water for the dry season ahead. Exactly the water supply Californians depend on every summer. A warm Pineapple Express does something almost the opposite. While traditional cold winter storms out of the North Pacific build the Sierra snowpack, atmospheric rivers tend to be warm. And though snow may still fall at the highest elevations, rain usually falls on the snowpack at lower elevations, which can quickly prompt melting, runoff, and flooding, and decrease the snowpack needed for California's water supply. The storm doesn't just add new water. It liquidates water that was already safely frozen in the mountains, and sends both down the same rivers at the same time toward the same towns. Exactly how much damage that double load can produce is not theoretical. It is written into more than a century of California's own weather records, in numbers that get harder to believe the closer you look at them. History has been running this experiment for a very long time, and the results are on the public record going back over a century. During the second week of January 1952, a series of Hawaiian storms swept into Northern California, causing widespread flooding around the Bay Area And the same storms brought a blizzard of heavy, wet snow to the Sierra Nevada mountains, notoriously stranding the train city of San Francisco. 3 years later, in 1955, a follow-up round of these storms produced the greatest flooding in Northern California since the 1800s, with the greatest damage in the Sacramento Valley around Yuba City. Move forward to December of 2010, and a Pineapple Express system ravaged California from the 15th to the 22nd of December, bringing with it as much as 2 feet, about 610 millimeters, of rain to the San Gabriel Mountains. 2 feet of rain, in a mountain range that most of the year receives barely any rain at all, delivered inside a single week. By February of 2024, the pattern had lost none of its teeth. A single Pineapple Express dropped so much rain on downtown Los Angeles that in just 3 days, the weather station in downtown Los Angeles recorded 216 millimeters of rain in just 3 days, equivalent to 60% of the city's average annual rainfall. Convert that into something you can actually feel. Imagine collecting 60% of an entire year's rain for one of the driest major cities in the country and having it all arrive over a single long weekend. That is not an unusually wet season. That is an entire season's water bill compressed into 72 hours. And it is what earns this storm type its second, less playful nickname among forecasters, an atmospheric fire hose, aimed and left running. But every one of those fire hoses was aimed by an ocean that keeps getting warmer, and that fact turns this whole account from a history lesson into a live, ongoing measurement. Every one of those past storms, 1952, 1955, 2010, 2014, 2023, 2024, happened on a planet that was, on average, cooler than the one we're living on right now. The ocean supplying the moisture for the next Pineapple Express is warmer than the ocean that supplied the last one. Warmer water evaporates faster and holds more vapor above it, which means the raw fuel available to the next storm is not the same fuel that powered the storm of your parents' or grandparents' generation. Scientists needed to know exactly how much water one of these systems could actually carry at its peak, not estimated from satellite images, not modeled from a desk, but measured directly, inside the storm, while it was happening. That meant putting people and instruments into the sky, flying straight into the heart of a river no one could see, to find out if the numbers on the page matched the monster in the clouds. What one research flight recorded out over the North Pacific turned out to be so far beyond expectation that, for a moment, the team reviewing the readout assumed their instrument had malfunctioned. To get that number, you cannot just stare at the storm from the ground and guess. You have to fly into it, drop instruments through it, and measure it from the inside. The same basic instinct that sends hurricane hunter aircraft punching through the eye wall of a hurricane. Except here there is no eye, no calm center, just an endless corridor of moving vapor, stretching to the horizon in both directions. This is the work of a NOAA research program called CalWater, and its signature tool is something almost comically simple. A small instrument called a drop sonde, released from an aircraft that free falls through the storm on a tiny parachute, radioing back readings of temperature, humidity, wind, and pressure the entire way down. Picture a flight scientist, call her Ellen, one of the researchers who has spent entire winters aboard aircraft chasing these systems out over open ocean, watching the drop sonde data scroll past in real time as the plane crosses back and forth through an atmospheric river's densest core. The instrument isn't measuring rainfall, it's measuring transport, how much water vapor is physically moving through a given slice of sky every single second. Like a checkpoint counting cars on a highway, except the highway is the atmosphere, and the cars are billions of gallons of suspended moisture. The study found that total water vapor transport in an atmospheric river averaged nearly 500 million kilograms per second, which is 2.6 times larger than the average discharge of liquid water from the Amazon River. Read that again, slowly. because it deserves a second pass. Not the Mississippi this time, the Amazon. The single largest river on the surface of the Earth, responsible for roughly 1/5 of all the fresh water that empties into the world's oceans. And the average atmospheric river, measured by these research flights, was moving 2.5 times more water than that, except it was doing it 1.5 miles above the ocean's surface, entirely as vapor, entirely invisible, entirely unnoticed by anyone standing on a beach below it. Translate the raw figure into something your body can actually register. 470 million kilograms of water, moving past a single point in the sky every second. That's something in the neighborhood of 500,000 metric tons, gone in the time it takes you to blink. It is the equivalent of draining a fully loaded oil supertanker, one of the largest vessels human beings have ever built, dry, and then immediately refilling it and draining it again, roughly once every 2 seconds, for hours on end, sometimes for days. That is not a rainstorm. That is closer to a planetary scale plumbing failure, except nothing is failing. This is the system working exactly as designed. The width of an average atmospheric river core measured by these flights came out to roughly 890 kilometers, give or take about 270 kilometers, or in miles, roughly 550 miles, give or take 170 miles. In other words, a moving column of concentrated water vapor wide enough to stretch from Los Angeles to well past Salt Lake City, carrying more water than the Amazon. This is the number that turned atmospheric rivers from a curiosity into one of the most closely tracked phenomena in modern meteorology. It is also the number that raises the uncomfortable question sitting underneath everything we have covered so far. If an ordinary atmospheric river already outperforms the largest river on the planet, what exactly happens when the ocean supplying the fuel keeps getting warmer? And how do you even begin to rank a system whose baseline already sounds like an exaggeration? Scientists needed something like the Saffir-Simpson scale used for hurricanes, a way to say in one glance whether the next atmospheric river bearing down on the coast is a nuisance or a catastrophe. Building that scale meant confronting a much stranger engineering question first. How does the atmosphere hold that much water in the first place without simply collapsing under its own weight? And the answer to that question is where the real machinery of this whole system finally comes into view. An atmospheric river should, by every intuition you have about spilled liquid, spread out. Pour water on a flat floor, and it doesn't travel in a tidy line. It fans out in every direction until gravity and friction settle it into a shapeless puddle. The atmosphere has no walls, no banks, no channel cut into rock to keep moisture moving in one disciplined direction for thousands of miles. And yet it does exactly that, winter after winter, storm after storm. So the real question, buried under everything we've covered so far, is this: what is holding the river together? The answer has nothing to do with solid ground and everything to do with pressure and temperature acting like invisible banks. Ahead of the cold front in a mature Pacific storm system, there's a narrow, fast-moving current of air, low in the atmosphere. Meteorologists call it the low-level jet, riding along the leading edge of what's known as the warm conveyor belt, the flow of air being lifted up and out of the storm's warm sector. That current does two things at once. It concentrates the moisture into a tight ribbon instead of letting it spread, and it drives that ribbon forward at speed, sometimes over 60 miles per hour, about 97 kilometers per hour, faster than the storm itself is moving. Think of it less like water on a floor and more like water forced through a fire hose nozzle. The nozzle isn't a physical object here. It's the pressure gradient between the front's cold and warm sides, squeezing the flow into a corridor the same way your thumb over a garden hose narrows the stream and sends it twice as far. The moment that pressure gradient weakens, the moment the front decays, or the jet stream buckles into a different shape, the nozzle effect disappears, and the river does exactly what water on a flat floor does. It fans out, loses coherence, and falls apart into ordinary scattered rain. This is why atmospheric rivers have a lifespan. They are born where the temperature contrast is sharp. They travel as long as that contrast holds together across thousands of miles of open ocean, and they die the moment the atmosphere around them evens out. Some die quietly over open water and never reach any coastline at all. Others survive the entire crossing and slam directly into a mountain range still at full strength. And what happens next depends entirely on how strong that river was when it arrived, which is precisely the kind of question a pilot flying drop zones through the core of one cannot answer with a gut feeling. It needed a number, and it needed a scale. Ranking a hurricane is old, familiar science. The Saffir-Simpson scale has been sorting storms into 5 boxes since the 1970s, and by the time a name like Category 4 reaches the evening news, everyone already knows roughly what kind of danger that number represents. Atmospheric rivers had no such shorthand until strikingly recently. A researcher could look at a satellite loop and correctly identify that a river of moisture was inbound. But there was no agreed way to say, in a single word, whether this particular one was going to top off a reservoir nicely or tear a hillside off its foundations. That gap closed in 2019 when Marty Ralph, the director of the Center for Western Weather and Water Extremes at Scripps Institution of Oceanography, the same research effort behind those dropsonde flights, led the team that built the first formal atmospheric river ranking scale. It runs from 1 to 5, mirroring the hurricane scale on purpose, so the public would have an instant, intuitive sense of stakes. The categories are built from 2 ingredients working together: how much water vapor the river is transporting at its peak, and how long that peak intensity holds up once the storm makes landfall. A short, sharp pulse and a long, grinding soak can carry very different consequences, even at similar strength, and the scale tries to capture both. This new scale separates itself from almost every other severity system in meteorology in one particular way, and it's worth sitting with for a moment. A Category 1 atmospheric river is officially described as mostly beneficial. It's the gentle, welcome soak that refills reservoirs, packs the snowpack, and quietly ends a dry spell without putting a single person at risk. Nothing else on the danger scales we use for hurricanes, tornadoes, or earthquakes has a rung explicitly labeled good. Move up to Category 3 and the balance tips, mixing benefit with hazard. By Category 4, you're mostly looking at hazard with some benefit still baked in, and Category 5 is described plainly as primarily hazardous, the atmospheric equivalent of a system that has stopped doing the state any favors and started simply taking things apart. The events we've already walked through in this story map cleanly onto that new scale, retroactively. The February 2024 storm that dumped 60% of downtown Los Angeles' average annual rainfall in 72 hours registered at the high end of that range, a Category 4 to 5 event, depending on the location measured. Which raises the obvious next question. If researchers now had a working scale, what happened the very next time California didn't get hit by just one of these systems, but by an entire parade of them, one after another, with barely enough time between storms for the ground to drain? That question stopped being theoretical almost immediately. Beginning the day after Christmas in 2022 and continuing for the next 3 weeks, California was struck by 9 separate atmospheric rivers in rapid succession. Not 9 storms scattered across a normal winter, but 9 landfalls compressed into roughly 3 weeks, each one arriving before the state had recovered from the last. This is the sequence that produced that wettest 3-week stretch in 161 years we opened this story with. And by the time the parade finally broke, the toll on the ground was staggering in ways that had nothing to do with a single dramatic image and everything to do with sheer accumulation. Follow the dates, because the order matters. Around December 27th, the first major system made landfall near the Bay Area, dropping the opening flood warnings of the sequence. By the end of the first week of January, the Sierra Nevada snowpack, tracked by state water surveys as running close to its seasonal average, jumped toward nearly 200% of its historical average for the date, an entire winter's worth of frozen water supply banked in roughly 10 days. Around January 11th, a levee along the Pajaro River in Monterey County gave way in the middle of the night, sending floodwater through the town of Pajaro so fast that residents described wading out of their homes in the dark with the water already at their waists. Statewide, the human cost of the sequence climbed past 20 deaths before the storms finally relented in late January, ranking it among the deadliest winter storm sequences in California's modern record. Estimated damage across the state ran into the tens of billions of dollars. And this is the part of the ledger that should genuinely unsettle you, because it sits at the very center of the whole story, not somewhere off to the side of it. Those same 9 storms, the ones that killed people and broke levees and buried the town of Pajaro in floodwater, also ended a punishing multi-year drought almost overnight. Lake Oroville, California's second-largest reservoir, which had sat at skeletal, sun-cracked lows for 2 straight years, rose more than 100 feet, over 30 meters, in a matter of weeks. Statewide reservoir storage went from crisis to comfortable in less time than it takes to plant and harvest a single crop. California's entire water system, the one that irrigates a huge share of the country's fruits and vegetables and supplies drinking water to tens of millions of people, was saved by the exact same weather event that drowned Pajaro. That is the uncomfortable inheritance California lives with every winter now. The same mechanism that fills the reservoirs is the mechanism that floods the towns. And there is no way to order up one without risking the other. Which forces the hardest question this story has to answer. If an ordinary atmospheric river already outperforms the Amazon, and if a mere 9-storm parade could produce the wettest 3 weeks in 161 years, what happens as the ocean supplying every one of these systems keeps climbing in temperature? Is this parade a preview of the new normal? Or was it simply an unlucky roll of the dice on an atmosphere that hasn't fundamentally changed? The physics gives an answer, and it isn't comforting. But it also isn't mysterious. It comes down to a relationship chemists and physicists have understood since the 1800s, long before anyone had heard the term atmospheric river. Warmer air holds more water vapor, not a little more. For roughly every 1 degree Celsius of warming, about 1.8 degrees Fahrenheit, the atmosphere's capacity to hold water vapor increases by about 7%. That relationship has a name, the Clausius-Clapeyron relation. But you don't need the name to feel the consequence. Picture a sponge. A cool, stiff sponge can only absorb so much water before it's saturated and starts to drip. Warm that same sponge slightly, and something in its structure loosens. It can now soak up noticeably more before it reaches its limit. The atmosphere behaves the same way. It is the sponge, warming, and every degree it warms means it can carry that much more water aloft before it has to let go of it. The planet's atmosphere and oceans have already warmed by a bit over 1 degree Celsius, close to 2 degrees Fahrenheit, above the levels of the late 1800s. Run that through the 7% per degree relationship, and the atmosphere feeding every Pacific storm system today is already carrying roughly 8 to 9% more available moisture than it was carrying when your great-grandparents were alive. That is not a future projection. That is the fuel supply the sky is working with right now, this winter. The one currently unfolding as you're watching this. And a major climate review, published just a few years ago, modeled exactly where that fuel supply is headed next, producing a projection that makes the 9-storm parade of 2022 look almost modest by comparison. A major review, published in Nature Climate Change in 2020, led by climate researcher Ashley Payne, alongside colleagues studying atmospheric river behavior worldwide, pulled together the modeling evidence and reached a conclusion that reads almost like a warning label. Atmospheric rivers are projected to grow longer, wider, and carry substantially more water vapor as the planet continues warming, even as the number of distinct storm systems making landfall may not increase very much at all. That distinction is the one that should stop you. It's not that California is necessarily going to get hit by more atmospheric rivers each winter. It's that each one arriving is being loaded with more water before it ever reaches the coast. Under a high-emissions future, some of the modeling work behind that review points toward increases in vapor transport approaching 30 to 40% by the end of this century, compared with today. Take the Amazon beating transport numbers. measured by those research flights, and scale them up by a third, and you are no longer talking about an unusually wet season. You are talking about a fundamentally different category of storm, arriving on a coastline whose levees, reservoirs, and drainage systems were engineered for the atmosphere of a century ago, not the one bearing down on it now. There is a second half to this warming story that gets far less attention than the flooding, and it might be the more dangerous half, precisely because it looks, on the surface, like good news. A climate scientist at the University of California, Los Angeles, named Daniel Swain, has spent years documenting a pattern he calls hydrological whiplash, the tendency for a warming climate to compress California's water supply into shorter, more violent bursts, separated by longer, drier gaps. The 9-storm parade of 2022 into 2023 didn't happen in isolation. It followed one of the driest 3-year stretches in the state's recorded history, and it was followed, in turn, by dry months that let the landscape bake again before the next system arrived. The reservoirs get their water, the drought technically ends, but the infrastructure built to manage a steady, moderate flow of rain across an entire season is instead being asked to absorb an entire season's water delivered in a handful of days, with nothing in between. And that is a very different engineering problem than the one California's dams, levees, and flood channels were designed to solve. Some of that aging infrastructure has already been tested past its limit once before, decades before anyone was using the phrase atmospheric river at all. And the warning it left behind, half buried in a 1986 emergency report about a river most Americans have never heard of, reads today less like history and more like a forecast nobody wanted to write down. The report itself was not dramatic. It was the kind of document that gets filed, stamped, and forgotten. A technical assessment produced by the Army Corps of Engineers in the years before 1986, quietly concluding that a long stretch of levee along the Yuba and Feather rivers, downstream of where the Bear River adds its own flow into that system, did not meet the standard required to hold back a major flood. The word used in similar Corps assessments from that era was inadequate, not failing, not urgent, inadequate, a bureaucratic word filed away in a cabinet in Sacramento, attached to a levee that thousands of people in the towns of Linda and Olivehurst were sleeping behind every single night without knowing the word existed. Then, in February of 1986, an atmospheric river arrived that made that word feel almost like an understatement. It wasn't one storm. It was a rapid sequence, remembered now as the President's Day storm, that dropped rain onto a Sierra Nevada snowpack still holding the season's early snow. And warm rain falling on cold snow does something a dry storm never could. It melts everything at once and sends the meltwater downhill alongside the rain that's already falling, doubling the load a river channel has to carry in a matter of hours. The Yuba River rose past every level the levee near Linda had been built to hold. In the middle of the night, the levee gave way. Roughly 24,000 people had to be evacuated from Linda and Olivehurst as the floodwater moved through homes that, hours earlier, had seemed nowhere near a river at all. That detail should stay with you longer than the flood itself. The Corps report warning about that stretch of levee wasn't a lucky guess written after the fact. It existed before the storm, sitting in a filing system, describing almost exactly the failure that was still years away from happening. The warning was correct. It simply arrived years before anyone treated it as urgent. And that gap between knowing a levee will fail and actually fixing it is not a 1986 problem. It is the exact same gap California is living inside right now, except the levees in question are older. The atmospheric rivers feeding them are carrying more water than they did in 1986, and the reports sitting in filing systems today are not describing a hypothetical flood decades away. They are describing a flood that some engineers believe could begin filling the same valley again with almost no advance warning at all. Because the Yuba Feather system wasn't an isolated case of bad luck, it's a symptom of a design problem baked into the entire Central Valley, and the scale of what that design problem could unleash under the right, or rather the wrong, atmospheric river sequence has already been calculated in exhaustive, unsettling detail by a team that decided to stop asking, what happened in 1986, and start asking, what happens if California gets the worst version of this that the historical record actually contains? That historical worst case has a real date attached to it, the winter of 1861 into 1862, a relentless sequence of storms, which climate scientists now retroactively identify as a chain of atmospheric rivers, struck California over roughly 43 days and turned the Central Valley into what eyewitnesses at the time described, without exaggeration, as an inland sea. Contemporary accounts describe a body of water stretching close to 300 miles long and 20 miles wide, about 480 kilometers by 32 kilometers, swallowing farmland, towns, and roads under a single continuous sheet of floodwater. The damage was so severe and so widespread that California's state government, headquartered in Sacramento, had to physically relocate to San Francisco because the capital itself was underwater. The newly inaugurated governor, Leland Stanford, is remembered in a story retold across California for a century and a half as having to travel to his own inauguration by rowboat because the streets of Sacramento had become a canal. The flood bankrupted the young state and reshaped how Californians thought about the Central Valley for a generation. Right up until the memory faded, the levees were built, the land was farmed, and the whole basin quietly filled back up with people who had no reason to think of the ground beneath their homes as the floor of a lake that had already existed once before. In 2010, the United States Geological Survey's Multi-Hazards Demonstration Project, led by seismologist Lucy Jones, alongside climate researcher Michael Dettinger, decided to ask what would happen if a storm sequence with that same historical intensity struck the Central Valley today, not with 19th century farmland and wooden levees, but with the actual current population, infrastructure, and economy of modern California sitting in its path. They called the resulting scenario Arc Storm, and the number it produced stopped a lot of people cold. The modeled scenario put total damages in the neighborhood of $725 billion, a figure roughly 3 times higher than the projected losses from the equivalent worst-case earthquake scenario modeled for the very same region. An earthquake plan gets headlines. A flood plan of similar magnitude, quietly filed under a name that sounds like a fantasy novel, barely registers outside a small circle of emergency planners. This is the detail that should genuinely stop you, because it separates Arc Storm from every other worst-case disaster scenario sitting in a government drawer. This wasn't science fiction. It wasn't an invented catastrophe designed to scare budget committees into funding. Every storm sequence used to build the Arc Storm model was assembled from real, previously observed atmospheric river events, stitched together into the kind of sequence the historical and geological record shows has already happened at least once, in 1862, and left physical evidence of happening multiple times before that in the sediment layers scientists have since pulled from Central Valley riverbeds. This wasn't inventing a monster. It was describing one that had already visited and simply asking what its return address would look like now. By 2022, researchers including climate scientist Daniel Swain revisited the scenario with an update sometimes called Arc Storm 2.0, folding in decades of climate warming that the original 2010 study hadn't accounted for. Their conclusion was not reassuring. A modern repeat of an 1862-style storm sequence, they found, could now produce even greater total precipitation than the original event, precisely because of the same warming atmosphere mechanism we've already traced through this entire story. A warmer sky simply able to carry, and eventually release, more water than the sky of 1862 ever could. Which raises an almost unbearable question hanging over California's aging levee network right now. If the tool used to hold back the water was built to withstand the storms of the past, and the storms arriving today are already measurably stronger than the ones that tool was designed for, what exactly is standing between the Central Valley and its own history repeating itself? And who, if anyone, is watching closely enough to see it coming, with enough lead time to actually matter? The people trying to answer that last question don't work behind a desk. They work at cruising altitude, 39,000 feet above the open Pacific, inside a converted jet aircraft with no windows in the cabin and a payload bay stacked with small, tube-shaped instruments, waiting to be dropped through the ceiling of a storm nobody on the ground can see coming yet. This is the operational heart of a program called AR Recon, Atmospheric River Reconnaissance, a joint effort between NOAA, the Air Force Reserve's 53rd Weather Reconnaissance Squadron, and the same Scripps Research Center behind the earlier dropsonde flights we walked through, the Center for Western Weather and Water Extremes, still led by its founding director. Every winter since the program went fully operational, these aircraft fly out over the open Pacific, sometimes more than 1,000 miles offshore, hunting for atmospheric rivers before they've made landfall. Not to study them out of curiosity, but to feed real, physical measurements directly into the same forecast models that decide whether California issues a flood watch 3 days out or 3 hours out. Picture the difference between forecasting rain by watching clouds from your porch and forecasting rain by sending someone up into the cloud itself to physically weigh the water it's carrying. That's the leap AR Recon represents. Before these flights existed, forecasters were largely estimating an incoming atmospheric river's strength from satellite imagery, a view from above that tells you an enormous amount about a storm's shape and moisture content, but almost nothing about the fine-grained structure hiding inside it, the exact core where the transport is heaviest, the narrow band within the band where the real danger is concentrated. Satellites see the shape of the river. Dropsondes measure its actual current. The payoff of that difference showed up in the forecasts themselves. Studies evaluating the impact of these reconnaissance missions found that assimilating dropsonde data from AR Recon flights measurably improved forecast accuracy for landfalling atmospheric rivers, in some cases meaningfully sharpening predictions of exactly how much rain would fall and exactly where, in the critical 72-hour window before landfall, the same window that determines whether a levee operator has time to reinforce a weak point, whether a reservoir manager has time to release water ahead of an inflow surge, whether a town like Pajaro gets an evacuation order 6 hours before the water arrives, instead of 6 minutes. That 72-hour window is not an abstraction. It is the entire difference between a flood you saw coming and a flood you didn't. And every dropsonde released from 39,000 feet over open water is, in a very literal sense, borrowed time, delivered back to the people standing on the coast below, before the river they can't yet see has finished deciding how strong it's going to be by the time it gets there. So where does all of this leave California, right now, this winter, as you're watching this? The honest answer is that the picture is being written in real time, by agencies whose entire job is to watch these signals before the public ever needs to. NOAA's Climate Prediction Center tracks the broader ocean atmosphere patterns, including the presence or absence of El Niño and La Niña conditions in the tropical Pacific, that tend to steer where atmospheric rivers aim their strongest landfalls each winter, while California's Department of Water Resources runs the flood forecast operations that translate incoming storm data into actual reservoir releases and levee inspections along the same river systems that failed in 1986 and nearly failed again in 1997. None of these agencies are predicting doom. What they are doing, consistently, is describing a system that has become measurably more energetic than the one their own infrastructure was designed to handle, and adjusting their vigilance accordingly. Framing this as a certain disaster would be dishonest. What the science actually offers is a trend, a direction, not a prophecy. Nobody can tell you months in advance whether this specific winter will bring a quiet, beneficial Category 1 soak that tops off the reservoirs without incident, or another 9-storm parade that tests every levee in the Central Valley at once. What the science can tell you with real confidence is the direction the dial is turning. The ocean supplying the moisture is warmer than it was in 1986, warmer than it was in 1962, warmer than at any point in the instrumental record. The atmosphere above it can hold more water than it could for any previous generation of Californians who built the levees, drew the flood maps, and decided how tall a wall needed to be to feel safe. And the storms riding in on top of that warmer, wetter atmosphere are arriving with a fuel supply that keeps quietly increasing, 1 fraction of a degree at a time, whether or not anyone happens to be watching the ocean that week. Go back to that gray brushstroke on the satellite map, the one that looks like nothing more than spilled ink drifting toward the coast. It has no eye, no name assigned by a hurricane center, no siren sound built into its arrival the way a tornado warning has one. It simply arrives, quietly, the way weather always has, carrying inside its narrow, invisible width more water than the Amazon, aimed at a stretch of coastline that has already been drowned once before, rebuilt and populated again by people who mostly don't know the name for the thing that's coming until it's already raining. The atmosphere is not creating a new kind of danger. It is simply turning up the volume on one that has always been there, 1 degree at a time, one winter at a time. And out over the Pacific right now, another one is almost certainly taking shape, gathering its moisture from a warm patch of ocean no different in principle from the ones that fed every storm in this story, waiting only for the jet stream to point it somewhere, and for someone, somewhere, to be watching closely enough to see it before it arrives.